Hello friends. So today we are going to solve questions from chapter Heat and Thermodynamics, and the questions which we are going to solve are from the year 2022, and total questions we are going to solve are 33, and all these questions are from the mains only. So this will be part 1 for the year 2022. In the part 2 we'll try to solve the remaining the questions as well as some advanced question also. So first question, it states that 0.056 kg of nitrogen is enclosed in a vessel at a temperature of 127 degrees centigrade. The amount of heat required to double the speed of the molecules is. So we have to find out the heat which is required to double the speed. So in this case we are given mass of the nitrogen is given to us, and we know that the RMS speed of the molecules is given as 3 RT divided by m and its square root. Okay. So we are going to use basic formula. So we can say that our VRMS is equal to 3 RT divided by m and its square root. And we can write this formula in initial condition and final condition. So let us say that initial condition, and for initial condition we assume that our temperature is our T1, okay, and therefore we can write that our VRMS 1 will be equal to 3R T1 m and its square root. And for our final condition, we are given, let us suppose that RMS 2 is a final condition, and this will be equal to twice of our initial condition, that is VRMS 1. So we substitute VRMS 1, or for final condition let us also assume that the temperature is T2. Therefore we can write this as our 3R T2 upon m square root is equal to 2 times square root of 3R T1 upon m, and here this square root, it cannot be cancelled out directly. We have to square both sides because there is 2 outside, so we can say squaring both sides, we get this will be our 3R T2 upon M is equal to 4 times 3R T1 upon M. And here this 3Rm cancels out, therefore we get that our T2 will be equal to 4 times T1. And T1 is given to us, that is 127 degrees centigrade, or we can say that will be equal to our in Kelvin 273, so this will be 400 Kelvin. Therefore we get T2 will be equal to 4 multiplied by our 400. This gives us that our T2 will be equal to 1600 Kelvin. And we have to find out that heat required to double the speed. Therefore we can say that heat required. Okay, so in this case also I forgot to mention one thing, that it is enclosed vessel, therefore we can say that the volume will be fixed. So we can say for enclosed vessel we have our volume is constant. Therefore we can use the formula that our heat required will be equal to Q is equal to N C of V multiplied by delta T, and N is our number of moles which we can find out. So we can say N is equal to number of moles, which will be equal to, we have our, it is given as 0.056. okay, so we can write it as our 0.056 and divide by 0.028. This gives us 2 moles. And then we are also supposed to find out C of V. So C of V will be equal to over F upon 2 times R, and F is our degree of freedom, so nitrogen is our diatomic. So we know that our nitrogen is diatomic, therefore degree of freedom will be equal to 5, that is value of F. Therefore C of V will be equal to 5.2 times R. And it is said that R is to be taken as 2, therefore we substitute the value of R as 2. So this 2 and 2 goes away, so this we get as 5. And delta T we can also find out. Delta T will be equal to our final temperature, which is our 1600 minus initial temperature, which is our 1400, giving us 1200 Kelvin. Now we can easily find out our Q. So we can say Q, number of moles we found out is 2 multiplied by C of V is our 5 and multiplied by 1200 Kelvin. So this will be coming as 12 kilojoules, 12 kilocalorie. So we get This will be over 12. Next question. It states that the relation between root mean square speed (VRMS) and most probable speed (Vp) for the molar mass m of oxygen gas molecule at a temperature of 300 Kelvin will be. So in this case, we have to, this is directly based on the formula. First we can write the formula for our VRMS. So we have a VRMS is equal to 3RT upon m square root, and most probable speed, that is our Vp, is equal to 2RT upon m and its square root. Temperature is same in the both cases, so we will keep it that as T and find out the ratio. So you can say their ratio, we have our VRMS Vp is equal to, this comes as our 3RT upon m, 2RT upon m and its square root. RTM cancels out, and this comes as square root of 3 by 2, so which gives us that our VRMS is equal to 3 by 2 square root multiplied by Vp. So we have 3 by 2 square root multiplied by Vp. Option B is correct. Next question. It states that the ratio of the specific heat C of P to C of V, which is gamma, in terms of degree of freedom N, is given by. So we know that our C of V is at constant volume, and so we can say our C of V will be equal to N upon 2 times R, and our C of P, which is our C of V plus R, and this comes as N by 2 plus 1 times R. So we need to find out the ratio. So we get their ratio, which is our C of P to C of V, will be equal to 1 plus N by 2 times R, and this comes as our N by 2 times R, and we can take N by 2 as common, so this will be coming as N by 2, and this will be about 2 by N plus 1 divided by R, and R we can just cancel out here, so we get this as our N by 2, and this N by 2 goes away, so we get the ratio of C of P to C of V will be equal to 1 plus 2 upon N. So 1 plus 2 upon N, option B is correct. Next question. It states that when a gas filled in a closed vessel is heated by raising the temperature by 1 degree centigrade, its pressure increases by 0.4%. The initial temperature of the gas is. So we are given that it is basically a closed vessel, therefore the volume will be constant. So you can say for closed vessel, our volume is constant. Therefore, we can say for ideal gas equation, which gives us that a PV is equal to nRT, and here we just said that our volume will be constant, N and R are already constant. Therefore, from here we can say that our pressure is directly proportional to temperature. Okay. And we have said that its pressure increases by 0.4%. Therefore, we can write that change in pressure oblique original pressure is of a 4%, 0.4%, so this comes as 0.04. Okay. And this happens when the increase in temperature is 1 degree centigrade. So it means at delta T is equal to 1, the temperature difference is 1 degree centigrade. So in terms of the Kelvin, the temperature difference will be still over 1 Kelvin. Okay. And if you use this relationship, so from here we can write that over P upon T is equal to constant. Okay. And we can also say that our delta P upon P will be equal to delta T upon T. And we know that delta P upon P is our 0.04 and delta T is our 1. So this comes as 1 upon T. Therefore, we at our T is equal to 1 upon 0.004. Therefore, we get our T is equal to 250 Kelvin. So we get T is equal to 250. Initial temperature is 250. Next question. A flask contains argon and oxygen in the ratio 3:2 in mass, and the mixture is kept at 27 degrees centigrade. The ratio of their average kinetic energy per molecule respectively will be. This is more or less dependent upon the formula directly. So let us first of all write the formula, and formula is our average kinetic energy per molecule. Let us suppose that is our Ke is equal to our 3/2 K multiplied by T. And we have two gases and we need to find out the ratio. Therefore, we can say kinetic energy for our argon to kinetic energy for our oxygen will be equal to 3/2 T temperature for argon and 3/2 K temperature for our oxygen, and they are at the same temperature. So the temperature of argon will be equal to temperature of oxygen, and this 3 kT also cancel out. So this comes as our 1. Or from here also we can see that kinetic energy is independent of their masses, which is here given as 3:2. It is only dependent upon the temperature, which in both cases is 27 degrees centigrade. Therefore, the ratio will be always 1:1. So option E is correct. Next question. It states that a mixture of hydrogen and oxygen has a volume of 2000 centimeter cube, temperature 300 Kelvin, pressure 100 kilopascal, and mass 0.76 gram. The ratio of number of moles of hydrogen to the number of moles of oxygen in the mixture will be. So we have to find out their mole ratio, and for that we can use the based on ideal gas equation, we can just try to sort out from there. Okay, so we know that the molar masses of hydrogen, so you can say our molar mass of hydrogen is 2 gram per mole, and molar mass of oxygen is 32 gram per mole. And we assume that the actual mass of the hydrogen in mixture, so we can say mass of hydrogen, let us assume that is our M1, and our mass of oxygen is our M2, and from here we can say that our M1 plus M2 mixture is of 0.76 grams, 0.76, and from here we can also calculate the number of moles for hydrogen. So we can say the number of mole of our hydrogen will be equal to our M1 divided by its molar mass, and number of moles of oxygen will be equal to M2 and divided by its molar mass, that is our 32. Okay. And now we can use our ideal gas equation. So you can say from ideal gas equation we have our PV is equal to nRT, and from here we can say our N is equal to PV divided by RT. Okay. So let's find out the value of N. So we get our N is equal to, pressure is given as 100 kilopascal, this is 100 into 10 to the power 3, volume is given as 20,000 centimeter cube, so that will be equal to 0.002, and R we know is our 8.31, temperature is said to be 27 degrees centigrade, 300 Kelvin. So from here we get that our N is equal to 0.0802 moles. And we can find out the molar ratio, and so we can say that our mole ratio which will be equal to our mole of hydrogen, mole of oxygen is equal to, we get this as M1 upon 2, M2 upon 32, which gives us, this will be our 16 M1 divided by M2, and total number of moles will be equal to number of hydrogen plus number of oxygen, and which we can write as M1 by 2 plus M2 by 16, and we just found out the total moles is our 0.0802, and we also know other equation also, we also know that our M1 plus M2 is equal to 0.76. So from here we can say that our M2 will be equal to 0.76 minus M1, and therefore we can write the equation that our M1 by 2 plus 0.76 minus M1 upon 16 is equal to 0.0802, and Okay, and now this is quite simple to solve only the multiplication. So we can say okay, let's multiply the entire equation by 32. So we get this as 16 m1 plus we are multiplying entire equation by 32. So this will be 16 m1 and this will be twice of our 1 second. One second. The LCM will be 16. Okay, so LCM will be 16, so this will be coming as 8 m1 plus 0.76 minus m1 is equal to 16 times 0.0802, and this comes as our 7 m1, I think. Okay, let me solve, then we can come back if it's creating problem. So this will be over 7 m1 and we are going to multiply, this is your 0.0802 multiplied by 16, that will be coming as 1.2832 minus 0.76, and this will be equal to over 0.52 and divided by 7. So this will be our therefore we get that our m1 will be equal to 0.074, and therefore our m2 will be equal to 0.076 minus m2 is 0.076, 1 second, 0.76, yeah, it's 0.76. So we have 0.76 minus and 0.76, this is 0.074, this will be giving us 0.068. Now we can find out our number of moles. So we get our number of moles for our H2, and H2 is our m1 by 2, so m1 is our 0.074 by 2, and number of our oxygen is our 0.068 and divided by 16. So this comes as 0.04 and 0.074 divided by 2. This will be 0.037. And we have to find out the ratio. Therefore, we can say that the number of our hydrogen to number of our oxygen is equal to, this comes as 0.037 divided by 0.04. So this comes as divided by 0.04, 0.92. I think I made some mistake somewhere. Okay, so it is given in ratio. The ratio this comes as 0.9 and 0.9. So I think it should be 1/3. And not 1/3, so it will be 1/16. Nope, not 1/16. I think I missed something. One second. So n is our 0.08. This looks good. Problem. So we have so this is our 32. My mistake. This is 32. And this is all 32. Entire calculation is wrong. Okay, sorry for that, I missed it. So we have 32, we multiply it by 32, so this gets our 16m1 plus, and now it will be our 0.76 minus m1 is equal to 32 times 0.0802, and obviously it will be double of my previous one, so that will be coming as now 2.5664, and it will be a 15m1. So we have 15m1 will be equal to 2.5664 minus 0.76, and we get this as 1.8. Therefore our m1 will be equal to 1.8 upon 15, which gives us 0.12 grams. Now it is correct. Now we can find out our m2. So we have m2 is equal to 0.76 minus 0.12, which gives us 0.639. Now we can find out our number of moles of our hydrogen, and that comes as our 0.12 divided by 2, which comes as 0.06, and number of oxygen is our 0.639 divided by 32, giving us 0.02. Now the ratio is correct one. Ratio is equal to number of moles hydrogen to oxygen is equal to 0.06 and 0.02. This comes as 3 by 1. Now it is correct. So option B is correct. I'm sorry for that, I missed it up. So we have option B is correct. Next question. It states that according to kinetic theory of gases, so we have to check these options one by one. So first states that motion of a gas molecule freezes at 0 degree centigrade. And so 0 degree centigrade is basically 273 Kelvin. But as long as temperature is greater than 0 Kelvin, they are free to move. Okay, so therefore this option is incorrect. And option B, the mean free path of the gas molecule decreases if the density of molecule is increased. And this is based on formula that of lambda is proportional to inversely to our density. So it means option B is correct. And option C, the mean free path is increases if temperature is increased and pressure is kept as constant. Okay. And so at constant pressure, we know that our density is inversely proportional to 1 upon temperature. Therefore, we can say our lambda is directly proportional to our temperature. So this option is also correct. And the average kinetic energy per molecule per degree freedom is 3/2 kBT for monatomic gas. Okay. And once again, average kinetic energy per molecule per degree of freedom is 3/2 kB of T. Okay. So for monatomic, we have to remember that it asks for average kinetic energy per molecule and per degree of freedom. Okay. And the standard formula is our average kinetic energy per molecule. This is our standard formula, and this is our 3/2 K multiplied by T. And this is true for our monatomic. And if we want to write this per degree of freedom, so we can write this as our average kinetic energy per molecule per degree of freedom. Per degree of freedom will be equal to, because the degree of freedom is 3, so this comes as our 1/2 K times T. Okay, so it cannot be 3. So this option is also incorrect. So we have our B and C is correct. So option B is correct. Next question. It states that what will be the effect on the root mean square velocity of oxygen molecules if the temperature is doubled and oxygen molecule dissociate into atomic oxygen. So here the oxygen is states to be into atomic oxygen. So this is directly based on the formula that our VRMS is equal to 3RT upon M and its square root. And here both things are varied. Here temperature is also changing, it is becoming double, and the molar mass is also changing because first it is oxygen molecule, then it is our atomic oxygen. Okay. Therefore, we can write that our initially we have our oxygen molecule Therefore, the mass of oxygen molecule is our 32, and temperature, we say it is our, we keep it T only. Okay. And finally, oxygen, atomic oxygen, so its molecular mass of atomic oxygen will be about 16, and our temperature is said to be doubled, 2T. Therefore, we can write that our Vrms for our oxygen will be equal to, this comes as 3R, and temperature is about 2T, and its mass is our 16 and its square root. So from here we can write that this will be equal to 16 goes by 8, so we get from here as 3RT divided by 8 and its square root. And in the first case, let me write the formula here. So we can say the Vrms of our oxygen will be equal to 3RT divided by 32 and its square root. So we simply find out the ratio. So we have a ratio, that is our Vrms for our oxygen to Vrms for our molecule will be equal to 3RT upon 8, and this comes as our 3RT upon 32 and its square root. At 3RT goes away, and this comes as 32 by 8, so which will be square root of 4 and coming as 2. Okay. So it means the velocity becomes double of, so option B is correct. So velocity becomes double. So you can say option B is correct. Next question. It states that a vessel containing 16 gram of hydrogen and 128 gram of oxygen at standard temperature pressure, the volume of the vessel in centimeter cube is. So we have our STP, and so we can need to find out its volume, and we have our, so let's find out the number of moles of hydrogen and number of moles of oxygen. So we can say our number of moles of our hydrogen will be equal to 16, and it is divided by 2, which will be coming as 8 grams, and number of moles of our oxygen will be our 128 given, and its molar mass, that is about 32, this will be coming as 4. Therefore, total moles will be equal to number of mole of our hydrogen and number of mole of oxygen, which will be, sorry, this is not gram, and this comes as 8 plus 4 giving us 12, and we are given STP. So we can say at standard temperature and pressure, we know that 1 mole occupies 22.4 liters, or in terms of centimeter cube, we can say that is equal to 0.400 centimeter cube. So this is for 1 mole, and for 12 moles let us call that as V. So this V will be equal to 12 multiplied by 400, and this will be approximately equal to 27 into 10 to the power 4. So option C is correct. Next question. A Carnot engine whose heat sinks at 27 degrees centigrade has an efficiency of 25%. By how many degrees should the temperature of the source be changed to increase the efficiency by 100% of the original frequency? So we can just draw the approximate figure of our Carnot engine. So we have a source, and that is going to provide heat for our engine, and on the other side we are going to have a sink, and this is going to do some engine is going to do some work done. And so it says that sink is at 27 degree and has efficiency of 25%. Okay, so we know that the efficiency, Carnot efficiency, that is nu is equal to 1 minus, and this is our T of C upon T of H, and so we can say from here initially we are given that efficiency is 25%, so this will be 0.25 is equal to 1 minus, and T of C is 27 degrees centigrade, that is 300 Kelvin divided by T of H, and from here we can say that our 300 divided by T of H is equal to 1 minus 0.25, which will be coming as 0.75. This gives us that our T of H will be equal to 300 divided by 0.75. So we get our T of H is equal to 400 Kelvin. And for the second case, it says that the efficiency should increase by 100% of its original efficiency. Therefore, we can say that our new efficiency let us call it mu prime is equal to our original is our 0.25. This is 0.25 multiplied by 2, which comes as our 0.5. Okay, it should increase 100%. And so we can write same formula, that is our 0.5 is equal to 1 minus, and this is our 300, and this is our TH prime, Therefore we can say that our Th prime, one second, so we can say that our 300 oblique Th prime will be equal to 1 minus 0.5, that will be our 0.5. Therefore Th prime will be equal to 300 oblique 0.5, and this will be equal to 600 Kelvin. So we have to find out the change in temperature. Change in temperature, that is our delta T, will be equal to 600 minus 400, giving us 200 Kelvin, and difference will be same, that is our 200 degree centigrade. So our increased by 200 degree centigrade, option B is correct. Next question. It states that a Carnot engine takes 500 kilocalorie of heat from reservoir at 727 degree centigrade and gives heat to the sink at 127 degree centigrade. The work done by the engine is. So we start with once again with the efficiency, because the efficiency of the Carnot engine can be written in two ways. One is our using the temperature, so we can say our efficiency, which is nu, is equal to 1 minus T of C divided by T of H, and so this comes as our 1 minus, this is 127 degree centigrade, so will be this plus 400, and 7 to 7 is going to give us 1000, so this comes as 0.6. And other way, we can also write that our efficiency is equal to work done divided by Q1. So from here we can say that our work done will be equal to efficiency times Q1, and efficiency is about 0.6. Heat supplied is 5000 kilocalorie, so this comes as our 3000 kilocalorie, and we can convert into joule because answer is joule, and we know that our 1 kilocalorie is equivalent to 4184 joules. Therefore we can say our work done will be equal to over 3000 multiplied by 4184, which gives us 12.6 into 10 to the power 6 joules. So option C is correct. Next question. It states that a monatomic gas performs a work of Q by 4, where Q is the heat supplied to it. The molar specific heat of the gas will be dash times R during this transformation, where R is the gas constant. So we have to find out the molar specific heat in terms of R basically, and gas is a monatomic, so we can say that for monatomic, we know that our C of V is equal to 3 by 2 times R, and we can use our first law, which gives us that the heat is equal to change in internal energy plus work done. And this is, or we can also write it as our N C of V delta T plus work done. And we are given that work done is our Q by 4. Therefore, we can say that our Q is equal to N C of V times T plus Q by 4, which can be written as Q minus Q by 4 will be giving us 3Q by 4 is equal to N C of V delta T. And so we can say our Q is equal to 4 by 3 N C of V delta T. And we have to find out the molar specific heat. Therefore, we can say that molar specific heat, which is C, will be equal to Q divided by N times delta T. So we substitute our Q, that comes as 4 by 3 N C of V delta T and N times delta T. Here N delta T cancels out, and we get that our C is equal to 4 by 3 times C of V, and C of V we know is 3 by 2 times R. So this comes as our 4 by 3, and this is our 3 by 2 times R. So this 3 and 4 goes by 2, so this comes as 2 times R. So it is about 2 times R. Next question. It states that the efficiency of the Carnot engine working between steam point and ice point will be. So here steam point and ice point means 273 degrees and 373, okay, Kelvin, not degree centigrade. And we know that our Carnot efficiency will be equal to 1 minus T of C upon T of H. 1 minus, we have this as temperature for cold is about 273 and temperature of hot will be our 373. And this will be equal to our 0.2681, or in terms of percentage we can say this will be equal to 26.81%. So option A is correct. Next question. It states that a thermally insulated vessel contains an ideal gas of molecular mass m and the ratio of specific heat 1.4. The vessel is moving with a speed v and is suddenly brought to rest. Assuming no heat is lost to the surrounding, the vessel temperature of the gas increased by. So it is moving, all of a sudden it stops, which means the energy gained by the motion will be converted into heat. So it means half mv square will be our change in the heat, or we can say change in the internal energy, because the rise in temperature is directly going to affect the internal energy. So we can say that our kinetic energy of gas will be over half mv square, and so this kinetic energy is our, so we can say this becomes internal energy, becomes internal energy, which is our delta of U, and that is given as n C of V times delta T. And specific heat ratio, that is our gamma, is given to as 1.4. So we know that our gamma is equal to C of P upon C of V is given to us as 1.4. And we also know that our C of P is equal to C of V plus R. Therefore, we can write that our C of P will be equal to, we can replace C of P by 1.4, C of V is equal to C of V plus R. From here we can write that our C of V will be our 0.4 times C of V is equal to R. And so we can say this is 0.4 times is equal to R. Therefore, C of V is equal to R upon 0.4, which gives us that our C of V will be equal to 5/2 times R. And so according to conservation, we can just equate them. So we can say our half m V square is equal to n C of V times delta T, and n is our number of moles. So we can say this will be our given mass, molar mass, and C of V is our 5/2 times R, and we have this as our delta T. And this given mass cancel out, so we get, and 2 also goes away. So from here we get our delta of T will be equal to, this is our mv square upon 5R. mv square upon 5R. So mv square upon 5R, option B is correct. Next question. It states that a heat engine operates with a cold reservoir at the temperature of 324 Kelvin. The minimum temperature of the hot reservoir, if the heat engine takes 300 joule heat from hot reservoir and delivers 180 joule of heat to the cold reservoir per cycle, is. So we can once again draw our, so we are going to have a source, and that is going to supply to the engine, which is going to do some work, and then it goes to our sink. And if the heat supplied by the source is our, let us call this source as our TH, so heat we call this as QH. HA means hot, and this is our cold, and QC. So efficiency we know we can write in terms of hot and cold as well as in terms of work done. So here we are interested in work done. Therefore we can say that our Carnot efficiency that is our nu is equal to work done upon our Q1. And work done, we can write this is work done will be difference in both heat. So that is the Q1 minus Q2 upon Q1. So this comes as our 300 minus 180 divided by 300. Okay. And okay, so here this is my Q1 and this is my Q2. Okay. So we get that our efficiency will be equal to 0.4. Now we can use our basic formula that our efficiency is equal to 1 minus our temperature of cold divided by temperature of hot. Efficiency we found out is our 0.4 is equal to 1 minus cold temperature is 324 and temperature of our hot. So from here we get this will be 324 upon temperature of hot is equal to 1 minus 0.4 will be about 0.6. So we get our temperature is equal to 324 upon 0.6, which comes as 540 Kelvin. It comes as about 540. Next question. It states that a diatomic gas gamma is 1.4 does 400 joule of work when it is expanded isobarically. The heat given to the gas in this process is. So basically it is isobaric process. So we can say that work done will be equal to, isobaric means pressure is constant P delta V. You can say for isobaric process we know that our work done is equal to P times delta V, or we can say this is our NR times delta T. And our so it is isobaric process, therefore we can write that the heat at constant pressure that is Q is equal to N C of P times delta T. Okay. And work done we already know, so we can just equate this work done is equal to about 400. Therefore from here we can write our N delta T is equal to 400 divided by N times R. So we substitute it here, we get our Q is equal to N and our C of P will be our 7 by 2 times R and delta T is our 400 times NR divided by NR. So here NR cancel out and this goes by 200. So we get our Q is equal to 1400 joules. So we get this is our 1400. Next question. it states that the total internal energy of 2 mole monatomic ideal gas at a temperature of 300 Kelvin will be in joules. So this is directly based on the formula. We know that for monatomic, our internal energy is equal to F by 2 times nRT, where F is a degree of freedom. So for this particular case, value of F is equal to 3. Therefore, our U will be equal to 3 by 2, number of moles is about 2, value of R is about 8.31, and temperature is 300 Kelvin. So this comes as our 74979. So we get here 7479 joules. Next question. It states that a sample of ideal gas is taken through a cyclic process ABCA as shown in the figure. It absorbs 40 joule of heat during part AB, no heat during BC, heat rejects 60 joule heat during CA. A work 50 joule is done on the gas during BC, during part BC. The internal energy of the gas at A is 1560 joules. The work done by the gas during the part CA is. So in this case, we can say that in part AB it says that it absorbs 40 joule of heat. So we can say that for AB we can write our delta Q of our AB, it absorbs is our 40 joules, and during CA it rejects 60 joules. Okay, so we can say our for our CA will be equal to minus of 60 joules, and work is done on the gas in the BC. Okay, so we can say work done during the process BC, and this is on gas. So this will be equal to our minus of 50 joules, and no heat during BC, so we can say our delta Q for our BC is equal to 0. And this is a cyclic process, so we know that for cyclic process our internal energy for complete cycle is equal to 0. So we can use our first law of thermodynamics. First law, it gives us that delta of U is equal to Q minus W. Okay, here W is work done by gas, okay, in the formula, that is by gas. And so we can say that our, because delta of U is 0, so this goes away, and we can write that our delta of Q for our entire cycle will be equal to 40 minus 60, which will be our nothing but delta of W, and which comes as minus of 20, and the work done for the entire circle We can also write this as work done for BC plus work done during our CA. Okay. Because here this AB is basically a constant volume, so work done during this BA will be equal to 0. Anyways, we can just write it if required, but that will be our work done for our AB. But this work done for AB will be equal to 0. So we can write the equation that our WBC plus WCA is equal to minus of 20. And so from here we can say our W of CA will be equal to minus of 20 and minus of our WBC. But WBC is our minus of 50. So this comes as minus of 50. And giving us this will be plus and this will be plus 30 joule. So option number B is correct. Next question. It states that a cylinder of fixed capacity 44.8 liters contains helium gas at standard temperature and pressure. The amount of heat needed to raise the temperature of a gas in the cylinder by 20 degrees centigrade will be. And this is fixed capacity is there, so obviously it is our constant volume. And it is saying about standard STP. Therefore, we can write that at STP, we know that our 1 mole, it occupies 22.4 liters. And therefore, we can find out the number of moles. We can say that number of moles, whichever n, will be equal to given capacity 44.8 and standard capacity, and this gives us 2. And we have our helium, which is monatomic. So we are given, we have a helium which is our monatomic. So for monatomic, we know that our C of V is equal to 3/2 times R. And we are having fixed capacity. We are given this that we are having fixed capacity. Therefore, volume is constant. Therefore, based on this, we can say that our heat Q will be equal to N C of V multiplied by delta T. And so number of moles are 2. So this comes as 2 multiplied by 3/2, and R is our 8.3. And it says that raise in temperature is 20 degrees centigrade. So delta T will be 20 Kelvin. So this will be 20. And here this 2 and 2 cancels out. And this will be 10 goes by 0. So this will be 6 multiplied by 83. And that will be coming as our 83, 18, 98. 498 joules. So option C is correct. Next question. It states that 300 calorie of heat is given to a heat engine. It rejects 225 calorie of heat. If the source temperature is 227 degrees centigrade, then the temperature of the sink will be. So in this case, we are going to use the formula for efficiency in terms of temperature as well as in terms of the heat. So first of all, let's solve in terms of heat. So we can say our Carnot efficiency that is our nu is equal to Q1 minus Q2 upon Q1, and this comes as our 300 and 225 minus 225 divided by 300, and this comes as 0.25. And we also know that our efficiency is equal to 1 minus temperature for the cold and temperature for the hot, which comes as 0.25. So we get this as our temperature of the cold, and source is our 227, so this comes as 500 Kelvin is equal to 0.75. This gives a T of C will be equal to 375 Kelvin, and we have to find out the degree centigrade. So from here we can say that our TC will be equal to 375 minus 273, which gives us 102 degree centigrade. Next question. It states that starting with same initial conditions, an ideal gas expands from V1 to V2 in 3 different ways. The work done by the gas W1 if the process is purely isothermal, the W2 process is purely adiabatic, W3 if the process is purely isobaric. Then choose the correct option. It should be the correct option. Okay, but anyways, so this is in general you can say related with the graphical representation. Okay, formulas are also there, but it is easy to interpret the result based on the graph, and that graph is our PV. So this is a pressure and we have a volume, and let us suppose it starts from a common point, and at this common point our volume is our Vi, and 3 processes are given. So first process is isobaric, so this will be an isobaric process, and here isochoric is not mentioned, but we can just draw it that also. So this will be our isochoric, and the graph of isothermal and adiabatic is almost similar. There will be a you can say minor difference in terms of the slope. Okay. And so therefore we can say that this one will be isothermal, which is having on the lower side, and we are going to have our this is our adiabatic. Therefore, and suppose they reach a common final volume. Okay. So we are given that for the same range of our volume, we can say that isobaric is our largest. So isobaric is our W3. So this work done will be our W3. Isothermal is our W1, and adiabatic is our isothermal, W2 is adiabatic. Therefore, we can say that our W2 is the least one. So we get this as W2 less than W1 is less than our W3. So we have W3 is the highest. Okay, that is highest in everybody. W1 and W2. So option D is correct. Next question. It states that two metallic box M1 and M2 of same area of cross section are connected with each other as shown in the figure. If the thermal conductivity of M2 is K, then the thermal conductivity of M1 will be, assume, steady state heat conduction. So they are basically connected in series. So we can say the thermal current will be same. So we can say thermal current is same. So if thermal current is same, we can write that our dq by dt, with respect to time, will be equal to, for our first part, that is delta T1, and we have this as our I1 upon its conductivity is said to be our, okay, let's assume K1 times A, and that will be equal to our, for the second portion, change in temperature, and we have this is I2 and this is our K2 times A. Sorry, this is not I1. L1 and L2, sorry. And so we can write that for our first case, delta T1 is our 100 minus 80, which is our 20. So let me write this as our 100 minus 80 divided by, we have this as our 16, and times K1. K1 is given as K. One second, we have given as M2 is K. Okay, so we can assume this is our K1 times area is equal to, and the second one is our 80 minus 0, and its thickness is 8 times, it is given as K times our area. So this area cancels out, and this 16 goes by 2, and we are left with 20 upon 2 is equal to, 20 upon 2 times K1 is equal to 80 times K. And this goes by 10, this goes by 0. Therefore, from here we can say that our K1 is equal to 8 times K. K1 is 8K. Option B is correct. Next question. It states that a 100 gram of iron nail is hit by a 1.5 kg hammer striking at a velocity of 60 meter per second. What will be the rise in temperature of the nail if 1/4 of the energy of hammer goes into heating the nail? This is once again the conservation of energy, because the hammer is having a velocity, so it is going to have a kinetic energy, and that kinetic energy, 1/4 of that goes into the heating part. Therefore, we can say that hammer kinetic energy is our half mv square, which comes as half 1.5, velocity is 60 whole square, and this comes as 2700 joules. And energy heating the nail, so we can say heat energy to the nail is equal to 1/4 of 2700, which comes as 675 joules. Therefore, we can use the formula that our heat, that is why Q is equal to mc times delta T, which comes as our Q is of 675, mass is given as of 100, and it's 0.42 specific heat, and rise in temperature delta T we are going to find out. So we can say that our delta T is equal to, this comes as our 675 divided by 42, which is approximately equal to 16.07 degree centigrade. Option C is correct. Next question. It states that an electric bulb is rated at 200 watt. What will the peak magnetic field at a 4 meter distance produced by radiations coming from this bulb, considering this bulb as a point source with 3.5% efficiency? So this is basically a combination of magnetic field and intensity, and so I think this question I have already covered in the magnetic field part also, but I can just solve it here also. So we know that efficiency is 3.5% and the bulb is rated for our 200 watt. So it means effective power of the bulb will be our 0.035 times 200. This comes as 7 watts. And we know that our intensity, which is I, is equal to power upon 4 pi r square. Here r is the distance. So power we just calculated is our P is our 7, and this is our 4 pi multiplied by 4 square. So this comes as 0.0348. And for EM wave, for electromagnetic wave, we know that our intensity I is equal to 1 upon 2 epsilon naught c, and this comes as E naught square, and our E naught is equal to, in terms of magnetic field, is our B naught times C. Therefore we can write that our intensity I will be equal to 1 by 2, and this comes as epsilon naught C cube, and this is B naught beta naught square. And so from here we can say that our beta naught will be equal to 2 times intensity epsilon naught C cube and its square root. Now we simply substitute the values. We get this as beta naught is equal to 2 times IV is our 0.0348, epsilon naught is our 8.85 into 10 to the power minus 12. C is the speed of light, that is 3 into 10 to the power 8 and whole cube and its square root. So this comes approximately as 1.71 into 10 to the power minus 8 Tesla. So option number B is correct. Next question. It states that, okay, this I've already done. So it states that in an experiment to verify Newton's law of cooling, a graph is plotted between the temperature difference delta T of the water and the surrounding and time as shown in the figure. The initial temperature of the water is taken as 80 degrees centigrade. The value of T2 as mentioned in the graph will be. So basic graph is given to us. So initially it said that the water is of 80 degrees centigrade, and this graph states that when our time is 0, the difference in temperature is 60. When time is 6 minutes, it is 40, and T2 it is given as 20. Okay. So we can write, because it directly mentions Newton's law of cooling, so we are going to use that particular equation or formula. So we can say our Newton's law of cooling, and we are going to write it in the differential form because we are interested in our this temperature difference. So we can Newton's law of cooling in differential form. And we can write that our rate of the temperature is equal to K T minus Ts, or you can simply write it as our delta of T divided by dt is equal to minus K delta of T. And this differential equation can be written in the form of our, because this is our, from the graph also we can see that the representation is like a exponential decay, And from, if you solve this differential equation, we are going to get its general solution as delta of t is equal to delta of t naught e raised to power minus k times t. And in this particular case, our delta of t naught is equal to 60 degree, which basically means at t is equal to 0 time. And our t of s will be equal to over 20 degree. So first of all, we are going to find out the cooling constant, which is represented as K. So therefore we can say from the graph we know that at T is equal to 6, we are having a temperature of 40, a temperature difference of 40. So delta of T is equal to 40 degree centigrade. So we get this as our 40 is equal to delta of T naught is over 60. So this comes as e raised to power minus k times 6. And so this 0 goes by 0. So this will be coming as 2 and 3. So we get this as 2 by 3 is equal to e raised to power minus 6k. Or we can say minus 6k is equal to natural log of 2 upon 3. So this comes as natural log of 2 minus natural log of 3, and which will be equal to minus 0.406. Excuse this. Therefore, we get cooling constant K will be equal to 0.406 divided by 6. So approximately it is equal to 0.06767 per minute. Okay. Now we find out our T2. Same formula, but now we know our cooling constant. So now in this case, our delta T is equal to 20 degree centigrade. Therefore we get 20 is equal to 60 e raised to power minus k T2, and this 0 and this goes by our 3. So we get this will be equal to our e raised to power minus k T2 is equal to 1 by 3. Or we can say this will be natural log of 1 by 3, and so we can say minus k T2 is equal to minus natural log of 3, which will be coming as minus 1.0986. Therefore we get our T2 is equal to 1.0986 divided by k, that is our 0.06767, which gives our T2 is approximately equal to 16.24 minutes. Okay, so answer is not given to us. This comes as 16.24 minutes. Next question. It states that a steam engine intakes 50 gram of steam at 100 degree centigrade per minute and cools it down to 20 degree centigrade. If latent heat of evaporation of steam is 540 calorie per gram, then the heat rejected by the steam engine per minute is. So we have to find out the heat rejected per minute. Okay. So here the heat will be rejected So we can say that the steam is at 100 degree centigrade and it cools down to 20 degree centigrade. Therefore, we are going to have two processes. One will be condensation, other one will be our cooling of water. Okay. So we have a condensation. For that, let us suppose heat of a Q1, which will be equal to m times L, and we have 50 grams, and latent heat is given to us as 540. So this comes as our 27,000 calorie. And then we come to the cooling of water. Which is our Q2, and that will be mc times delta T, and which comes as 51, and change in temperature is our 100 minus 20. Therefore, we get our Q2 is equal to 4000 calorie, and thus the total heat will be equal to Q1 plus Q2, which comes as 27,000 plus 4,000, and will be equal to 31,000 calorie, and 10 is power 3. So this comes as our 31 into 10 is power 3 calorie. So it will be over 31. Next question. It states that a solid metallic cube having a total surface area 24 meters square is uniformly heated. If its temperature is increased by 10 degrees centigrade, calculate the increase in the volume of the cube. So this is nothing but a volumetric expansion. And so we are going to use the formula for volumetric expansion. We can say our volumetric expansion, that is our delta of V is equal to V times beta times delta T, and beta is our volumetric coefficient, and we can write in terms of linear coefficient. We know that our beta is approximately equal to 3 times alpha, and volume is given, surface area is given to us as a 24. So we can say that total surface area for our cube is our 6a square, which is given as 24. Therefore, from here we can say our A is equal to 2 meters. Now we can find out the volume V. So we can say our volume V will be equal to A cube, giving us 2 cube, that is our 8 meter cube. Answer is in centimeter. So this comes as 8 into 10 to the power 6 centimeter cube. And alpha is given to us. So we simply substitute the values now in the formula. We get our volumetric expansion, that is delta V is equal to our V, and V is our 8, 10 to the power 6. Alpha is our 5 into 10 to the power minus 4, and this is 3 times alpha, so this comes as 3, and change in temperature is 10 degrees centigrade. Therefore, we get that our delta of V is equal to 1.2 into 10 to the power 5 centimeter cube. 1.5, sorry, 1.2, option B is correct. B is correct. Next question. It states that a copper block of mass 5 kg is heated to a temperature of 500 degrees centigrade and is placed on a large ice block. What is the maximum amount of ice that can melt? Okay, so it means the entire heat from the copper should be used in melting of the ice. Okay, so first of all, let's find out the heat from the copper. Heat from copper, which is a Q, let us call this as Q copper, will be equal to mass multiplied by C and delta T. Mass is given as 5 kg, so this comes as 5000. C is given to us as 0.39, and the temperature is 500 degrees centigrade. 500 minus 0. Therefore, we get our for copper is equal to, this comes as our 975 00 000, and we assume that the mass of the ice that is being melted by this particular heat is m ice. So we can say ice melting. Let us suppose that heat is of Q ice will be equal to mass of the ice multiplied by its latent heat. And according to conservation, this Q ice should be equal to, because entire heat is being consumed by the ice, so they should be equal. So this comes as our 975,000 is equal to mass of the ice multiplied by 355. So we get mass of ice is equal to 975,000 and 355. So approximately this will be coming as our 2.91 kg. So option C is correct. Next question. It states that a geyser heats water flowing at a rate of 2 kg per minute from 30 degrees centigrade to 70 degrees centigrade. If geyser operates on gas burner, the rate of combustion of the fuel will be gram per minute. Okay. So it means the heat that will be generated will be because of the burning of the gas. So there should be equal the amount heat that is being used to, you can say, raise the temperature of the water. Therefore, we can say that our heat required to increase the temperature, or we can say heat required by geyser. Let us call this as Qg is equal to mc delta of T. So we get the Q of G is equal to, we have this as 2000, specific heat is given as 4.2 multiplied by, this goes from 30 degrees centigrade to 70 degrees centigrade. -70 30. So this heat comes as our 336,000 joule per minute, and rate of combustion of the fuel. Okay, and we can say that our heat from gas burner let us call this as QB before burner, and this will be equal to our mass of our gas. Let us keep this, no, we cannot keep this M. Let us call this as MF times heat of combustion, that is 8 into 10 to the power 3, and our heat for the gas should be equal to heat that is being heat required by the geyser should be the heat supplied by the burner. So this theta G should be equal to theta B, and from here we can say this 336,000 is equal to our MF times 8 into 10 to the power 3, and this 3 and 3 goes away, so this will be 336 divided by 8. So we get that MF is equal to 336 divided by 8, and this will be equal to 4 and 2, 1642 gram per minute. So we get this as our 42. Next question. It states that a lead bullet penetrates into solid object and melts. Assuming that 40% of kinetic energy used to heat it, the initial speed of bullet is, so we have to find the initial speed. Okay, here also we are going to use the conservation, and the heat that is going to melt will be equal to, suppose, Q, and that will be equal to raise the temperature and then melting point. Okay, therefore we can say that heat to melt suppose is our Q, and that will be equal to over mc delta T plus m into L. Okay. And so we get our Q is equal to m we can take as common, and we are having the specific heat is 125 and temperature is 127 and 327. So this comes as our 327 minus 127 and plus latent heat is our 2.5 into 10 to the power 4. Therefore, we get that our value of Q is equal to 50,000 times M. And only the 40% of kinetic energy E will be converted into Q. So let's find out our kinetic energy. So we can say our kinetic energy is equal to our half m v square, and this is our, so according to the question, 40% of kinetic energy will be into heat, which in this case is our Q. Therefore we can write that our 0.04 times half m v square, Q is our 50,000 times m. Here m and m cancels out, and this comes as our 0.2. This will be our 25,000, and 25,000 will be our 500. So we get our V is equal to 500 meter per second. So option number B is correct. Next question. It states that resistance of the wire is measured at 2 ohm and 3 ohm at 10 degrees centigrade and 30 degrees centigrade respectively. The temperature coefficient of the resistance of the material of the wire is. So this is directly based on the formula. We have to find out the temperature coefficient of the wire, temperature coefficient of resistance, which is our alpha. And for that, we are going to use the formula that the resistance at a temperature of T is equal to R naught 1 plus alpha times delta T. Okay. And we have two values, so we can divide this formula into two parts. So first is at 10 degrees centigrade. We can say RT is given as our 2 is equal to our R naught 1 plus alpha, and temperature is our 10 degree. So this is multiplied by 10. Second, we are having 30 degree. So we have 30 degree centigrade. This is 3 ohm R naught 1 plus alpha times 30. We simply take their ratio, and we get this as our 3 by 2 is equal to R naught 1 plus 30 alpha R naught 1 plus 10 alpha. R naught and R naught cancels out, and we get this as, we cross multiply. So this will be our 3 plus 30 alpha is equal to 2 plus 60 alpha. And we manipulate it, we get this as our 1 is equal to 30 alpha. So we get alpha is equal to 1 upon 30. So approximately this is our 0.033 per degree centigrade. So we get this as 0.033. Option A is correct. Next question. It states that as per given figure, two plates A and B of thermal conductivity K and 2K are joined together to form a compound plate. The thickness of the plates is 4 cm and 2.5 cm respectively. The area of cross section is 120 cm square of each plate. The equivalent thermal conductivity of the compound plate is 1 plus 5 upon alpha times K. Then the value of alpha is. So both of them are in series. So we can say the thermal equivalent resistance is equal to the individual combination of their, that is our RTH1 plus RTH2. So we can say that our in series we can write that thermal equivalent resistance, you can say R equivalent thermal will be equal to, for our R1 thermal plus R2 thermal. Okay. So in terms of, because cross sectional area will be same, so we can write this as our L equivalent divided by K equivalent is equal to L1 upon K1 plus L2 upon K2. Area of cross section is the same. And here L1 is, so this is our L1 and this is our L2. Okay. And accordingly we have a K1 and this is our K2. So we get L1 is our 4 and K1 is our K plus L2 is our 2.5 and this is our 2K. And we can take 1 upon K as common. So this will be coming as 8 plus 2.5 divided by 2. And L equivalent, total length will be equal to our 6.5, that is our L1 plus L2. So this we get our 6.5 upon K equivalent is equal to 1 upon K, and this comes as our 8 plus 2, that is 10.5, and divided by 2 will be equal to 5.25. Once again, this is our 8, 10.5, yeah. So this comes as our 5.25. Therefore we can say that our K equivalent will be equal to 6.5 divided by 5.25 times K, which gives us 26 upon, okay, we have to do it in form of alpha fraction, so that will be 26 upon 21 times K. But we are given that our K equivalent is equal to 1 plus 5 upon alpha times K. So we can just equate it, and this will be equal to 26 upon 21 times K. Here K and K goes away, and here we get this as 1 plus 5 upon alpha is equal to 26 upon 21. So we get this as 5 upon alpha is equal to 26 upon 21 minus 1, which comes as 5 upon 21. And here 5 and 5 cancels out, which gives us that value of alpha is equal to 21. So alpha will be equal to 21. Next question. It states that at what temperature a gold ring of diameter 6.230 centimeter be heated so that it can be fitted on a wooden bangle of diameter 6.241 centimeter. Both the diameter has been measured at room temperature, that is 27 degree centigrade. So obviously this temperature of the ring is going to increase, and which is going to lead to its expansion. Okay, so we can say that the linear expansion and we can write this in terms of our diameter, that is our final diameter will be equal to our initial diameter, and this comes as 1 plus alpha, and this is our linear coefficient of linear expansion times delta t. Okay. So we substitute the values. Final diameter is our 6.241, initial diameter is 6.230, 1 plus alpha. Okay, let us write this alpha L. So alpha L is our 1.4 into 10 to the power minus 5 times delta t, and so we get this as our 1 plus 1.4 into 10 to the power minus 5 times delta t is equal to 6.241, and we have 6.230. This will be approximately 1.001767, and so from here we get 1.4 into 10 to the power minus 5 times delta t will be equal to minus 1, so this will be 0.001767, which gives us our delta t is equal to 0.001767, and this is 1.4 into 10 to the power minus 5. So we get our change in temperature is approximately 126.2 Kelvin, and we have to find out the what we have to find out at what temperature. Okay, and it is with respect to the room temperature, therefore we can say the final temperature 1 second. Okay, final temperature will be equal to our T is our 27 plus 126.2, which is approximately equal to 153.2, or option D. This is a closed one, so we can say 152.7. So we have option D is correct. So this complete all the, how much question we did? I think we did 33 questions. I think so. We did 33 questions for 2022 mains only. So this completes all the 33 questions from the year 2023. Thank you.